Yes, it is. So yesterday we had a review session. So please, I strongly recommend that you watch the things. We did very good problems. People asked very good questions. We were in the room, I think we were like 25, and online, I don't know how many we were. Something like that. So please, I recommend that you watch it. Okay, and I also strongly, like put 3 lines under strongly and in bold. Suggest that you attend the tutorials. Okay? From now on. I mean, you still have 3 left, okay? 3 or 4, I don't know how many. Two weeks, so maybe 6 tutorials, 5 tutorials left. So please, I strongly recommend that you go and watch them. And you go and attend them.
All of them or just one?
I mean, the more you could go to, the better they are, okay? I mean, your final is in first week. Take it as an hour of preparation. Okay, great. Awesome. Now, last time I forgot a proposition. I was proving let R be a ring with P elements, where P is prime, then R is isomorphic to Z mod PZ. Now, in the proof, I refer to a previous prop. The previous prop I didn't write, I forgot. Again, I was saying yesterday at 2 a.m. maybe I remembered that I had forgotten it. And then if you watch the recording, I was writing here, and then I looked at the previous prop. I had it erased. But yeah, I convinced myself that I did it, but I didn't do it. Now, the proof is still correct, just the previous prop isn't there. So what is the previous prop? The previous prop. Okay, so this should be inserted before this, here. Insert this one here. Very well, I should have written it downstairs. Okay, the previous proposition, it says that let R, or let n be bigger or equal than 2, and suppose that R is a ring such that 1R has order n in R plus, of course. Well, 1 makes sense in R star. Then R has characteristic n. Okay, so the proof of that, do you want to prove it or it's good?
Wait, isn't that the definition of the characteristic we gave?
No, the characteristic, what is the definition? It's the kernel of the homomorphism, right? From Z to R. Yeah.
So it's the size of the kernel?
No, it's the kernel. N, it's NZ, the generator of the kernel, the positive generator of the kernel.
Okay, so if it's NZ, it's the
N.
characteristic is N,
Yeah.
not NZ.
No, the kernel is NZ, the characteristic is N. Exactly. And N is positive. It's the unique positive number such that the kernel is NZ.
Yeah, but the characteristic
Is N.
a number.
Yes, I know.
And not a set.
Not a set. No, did I say it's a set?
But you said that it's the kernel, and a kernel.
Oh, no. Sorry. Yeah, I meant the generator of the kernel.
Gives it. Oh, okay.
Yeah, the generator, the NZ, where N is bigger or equal to 2 or N is 0.
Yeah.
Okay? Sorry for confusion. Yes?
But wouldn't that kind of be a definition that goes right for the left word?
Yeah, exactly. Those are equivalent. Exactly. Unless N is 0. Yeah.
Yeah.
So, well, proof. Let phi denote a unique ring homomorphism from Z to R. Now, I know that 1 has order n, right? Now, m belongs to curve phi. Let m be an n. Or, sorry, what do I say? Yeah, let m belongs to curve phi. If and only if what? Phi of m is 0R. If and only if m1r is equal to 0R. If and only if what? m, if and only if the order of one R in R plus divides M, if and only if M belongs to NZ. Okay? Here let M be Z. So kernel of I is equal to NZ. So R has characteristic N. Okay? So insert that before the proof, please, before the proof of the theorem. I mean, I've used it, right? I said that one has order P, so the kernel must be Pz of that homomorphism. Okay, great. Awesome. So, I mean, before you erase that, before you insert it, you can just write one more sentence. So, a big proposition. Let n be bigger or equal to 2. And let R be a ring. R has characteristic N. If and only if one R has order N in R plus. Okay? This is just the previous two statements combined today. Okay? Follows from the two props above. Okay, great. Now we'll move on to new stuff. We'll continue with this characteristic business, but we'll just continue with the new stuff. Okay? Did we see where to insert it? We inserted those two? Yeah? Okay. Great. Now, another proposition. Let R be a ring of characteristic N. Bigger or equal to 2. And let X belongs to R. The order of X in R plus divides N. Then the order of X in R plus divides N. Proof. What do? I take N times X, right? So N X, which is just X plus X N times. What is that? I can factor an X out here. I can write it as X times 1R plus 1R N times. Agree or not? You can factor an X, this is a ring, factor an X, you can write it as X times 1 plus 1 plus 1 plus 1. Now, if R has characteristic N, what is 1 plus 1 plus 1? It is 0, right? This is just X times 0R, which is 0R. Since N times 1R is equal to 0, since R has characteristic N bigger or equal to 2. Okay, great. And that's clear. Hence, the order of X divides N. Or hence X has finite order. And R plus. And it divides N. Okay? Let me see if I can. Are we good here? Great. prime number, and R a finite ring with characteristic P. Is this stuff clear? Is this stuff clear? Yeah? Is it clear? N times x is equal to 0. So x has order dividing n, right? X plus x plus x plus x n times gives you 0. So the order of x must divide n. Agree or not? Groups. Groups, right? Groups. No rings. Well, there is rings, but this is a group theory statement, yeah? Are we good here? Are we good or not? If I take n, any question on this one? Ask. Yes?
How come the order isn't just n?
Oh, it divides n. It could be less. Maybe it could be. Take the order of 0, for example. Okay? It's 1. It's 1, right? Take z mod 4 cross z2, for example. What's the characteristic of z4 cross z2? What's the characteristic of z4 cross z2? It's the order of 1, 1, right? The order of 1, 1 is the LCM of 4 and 2, right? Which is 4. Now take the element 0, 1 in z4 cross z2. What's the order of that? 2. So it divides 4. It's not necessarily 4. Okay? Great. Let me be a prime number. This statement you might revisit in 236 next term. Okay? You might revisit it in another way. And R, a ring of characteristic P, and R a finite ring. This is very important. Of characteristic P. Then R is equal to P to the M for some M in. Okay? So if you have a finite ring with prime characteristic, its only orders are powers of P. Okay? Very nice. The order of the ring, the number of elements of the ring is P to the M, if the characteristic is prime. Strong statement, right? Next term, you will prove this in a better way. You'll prove this in a better way. You'll prove this using vector spaces. Okay? Next term in Algebra 2, linear algebra, you'll prove this using vector spaces. Which is shorter proof, but you need more machinery. Yeah? Any questions? Depends on what they cover every year. Again, so the theory of finite fields is good with vector spaces. When you do vector spaces, then you can see finite fields in a very nice way. We won't do that. I'll try to take, try to avoid vector spaces. But let's prove this. By the previous prop, well, proof, let x be in R, and x different than 0 R. Then x has order dividing P in R plus, right? By the previous proposition. If I have a characteristic of n, then the additive order of x divides n. Now if the characteristic is P and x is non-zero, then x has order dividing P, right? Replace n by P. Look at there. Replace n by P, what do you get? X has order dividing P. Now what can I say? P is prime, so what is the order of x? And x is non-zero. X is not the identity element of addition. Then x has order P. Since P is prime, and x is different than 0R, then x has order P in R plus. So if you have a finite ring of characteristic P, every non-zero element, what is the order of it if P is prime? P. We agree or not? take a finite ring with characteristic P, or take any ring with characteristic P, we didn't use finiteness yet, then the order of x is P, right? You know that P, yeah.
Oh no, it's just like you always write R plus, but like it's the only group.
It's the only, well, I mean, because I'm worried that if x is a unit, for example,
Okay.
you can say that it's R star. Okay? When you say x has order, if x is a unit, then you can say the group of units. Right?
Okay.
If x is non-zero and R is a field, for example, you might confuse.
But it's always going to be under addition.
R is always under addition. Yes.
Sure.
Right? R is always under addition. That's right. Okay? Then x has order P in R plus. Then we agree with this statement or not? Do we see that? Yeah.
Intuitively, I feel like, how would x squared also have order p? I feel like x squared would have to have order less than
Well, x, you're talking multiplicatively, right?
I don't know.
You're talking x squared is x times x. So what you want to use is, you're using is the GCD formula, right?
Okay.
You're using the order of x squared is n over GCD 2n, right? This is what you're using, this is what you're referring to.
I got it.
Yeah, but here the x squared is a multiplicative group. So what you're really looking at is 2x. Right? It's x plus x, because the operation here is addition. So look at z mod pz, for example. Okay? Z mod pz. What is the order of 2 in z mod 5z? 5. What is the order of 1? 5. Your 2 is your 1 squared in here, because it's addition. It's 1, circle 1, because your circle is addition. Is that clear? That's why I say R plus always. I try to say R plus. Yes? Okay? In the additively. Yep.
I don't think it's recording.
You don't think it's recording?
It's not recording. I tried to join online, like at the start.
Oh, no, it's not online. I cut it online. Yeah, I cut it. It didn't work. Yeah. Sorry about that. I mean, everybody saw that it wasn't working, so. Yeah, so I'm just recording on my computer now. Okay? Any questions? Okay, now why does that say that if R is finite, so we agree with this, that any prime, the order of any non-zero element in R is P. Now if R is finite, why is it the case that R has size P to the M? Yeah?
Can't we use like Syllo's theorem and say that since it's
Very
prime,
good.
it's a subgroup?
Oh, sure, you can use Syllo's theorem. Very good. Or you can use something else, slightly lower than. You can use Syllo's theorem. You want to use? Oh, well, not Syllo's theorem. Let's use Cauchy's theorem.
Okay.
Cauchy's theorem. So suppose Q is a prime. That's what you want to say. You have a subgroup of order Q.
Yeah.
If Q is a prime divided. Yeah. Okay. Yeah. Suppose that Q is a prime dividing R, the size of R. Then by Cauchy's theorem, when you see algebra 2 with vector spaces, the proof becomes online. Anyways, by Cauchy's theorem, there exists y different than 0 r in R such that the order of y in R. So if I say the order of y in R, is it clear that R is under addition, or should I write under addition? Should I write it?
Yeah.
Okay. R under addition is Q. Agree or not? Cauchy's theorem tells you that if you have a prime number dividing the size of your group, then you have an element of order that prime number. Wait a minute. But any non-zero element, what's the order of any non-zero element? Here. If x is non-zero, what is the order of x? P. since any non-zero element has order P in R plus, then Q is equal to P. So what's the only prime dividing the size of R? P. The only prime dividing R is P. So R is equal to P to the M for some M in N. Of course, M is different than 0. M is bigger than 0 since since R is like, it's not the 0 ring, so because R has size bigger or equal to 2. Right? You have 0 and 1. Okay? Is that clear? Are we good? And we're just playing with the group statements here. Next term, I think it's going to be very nice if you see things like that. Finite fields, finite rings, yes?
Is algebra 2 the same as linear algebra?
Yeah. This is linear algebra. All that is linear algebra in disguise. But I'm just not saying it's linear algebra. Okay? All the theory of finite fields that you do in Algebra 1, you will extend it in Algebra 2 by just linear algebra. Okay? Okay, great. Are we good now? Is that clear? Yes, sir.
Right. But how like rings and fields present in linear?
Pardon me?
How like rings and fields present in linear algebra?
You'll see. Okay?
They weren't for me.
Depends. I don't know. Some, yeah. Okay, Chinese remainder theorem for rings for Z. Okay? This characteristic stuff I really like, so you know you can you might expect something like that on the exam, either a practice question, you know, a calculation, or a proof. This stuff I really like, so okay. You know the proofs are quick, so they're easy to grade. You know, top, it's quick, right? So you can expect a question like that. You can expect a question from characteristic. Proofs or calculations. Calculations or proof. Okay? Great. Okay, so please do know these. The proofs are very quick, right? I mean, we're going to do more. We're going to do more. We're going to do more linear algebra stuff. Well, not linear algebra stuff, but field stuff that you can revisit with it, that you will revisit with linear algebra. Hopefully next term, or the terms after. Okay. Great. Are you good now? Chinese room? Yes.
If P divides the size of R, why couldn't the size of R be P to the M times just another constant?
And if this other constant must have a prime factor, right?
Yeah.
Q. Now, if you have this Q, if by Cauchy's theorem, if Q is another prime dividing P, then you have an element of order Q, a non-zero element of order Q, a non-identity element of order Q. Now, what is the identity element? What is the only possible order for non-identity elements? It's P. So if Q is another prime dividing R, then R would have an element of order Q, then Q must be equal to P. Okay? So P is the only prime dividing. Yeah. Why can X be 1? The order of X, it could be 1, has order dividing P. Now, if X is non-zero, what's the only element of order 1? It's the identity element, right? So if X is not the identity element, then X has order, then X doesn't have order 1. Okay? Great. Yeah, I don't know if they, anyways. So let Mn be bigger or equal to 2, integers of course, and GCD Mn is 1. Then we had a statement for groups, then we'll do this for rings. But we'll do this in a very nice way. As rings.
you say this, the cardinality of R equals to P to the M for some M, but why is it not specifically just P to the 1?
Could be.
Yeah, but why, like, doesn't this say that this would just be order P?
Yeah, so take ZP, Z mod P, cross Z mod P, cross Z mod P. Every element has order P. Every non-zero element has order P.
Yes.
Take Z mod P, cross Z mod P, cross Z mod P, cross Z mod P 4 times. Every element, non-zero element has order P.
Yes.
Keep on going. So for every n, you can find a ring like that. It doesn't, P is not 1 necessarily. Okay? It's not, that doesn't tell you that P is 1. M is 1, sir. Is that clear? It tells you that P is the only prime dividing a number. If P is the only prime dividing a number, then this number is P to some power. Yeah?
Can you explain why the size of R and P
So R has two elements, 0 and 1 R. And these are distinct by assumption. Okay? So you have two elements at least in the array. So M can't be 0. So R can't have size 1.
Okay, if P to the power M times a constant, or K, and where did you see P and K? Why?
Very good. So this K must have a prime factor, right? Q, right? This K must have a prime factor, so you'd have an element of order Q. Okay? Yeah?
I'm trying to make it also imply the field.
I don't know. No, for parts of field, no, I don't like. I mean-
Why ring they're not fixed? Why ring is they're not fixed?
I mean, if you look at the depends. So if your n is prime here, if your n and m are prime, then this is a product of two fields. So you can let fields play into there, but it's not. Yeah. Okay. Are we good here? Let's prove that. Is this thing okay? Is this thing okay? Any questions on this? These are just like number theory statements. If P is the only prime dividing a number, then this number is some power of P. You cannot have any other prime dividing it. Yeah? Everybody. What's the only prime number dividing 25? 5. What's the only prime dividing 64? Sorry. What's the only prime dividing 64? 2. What's the only prime dividing 121? 11. Okay. 6. Can you find an element, a prime number, only one prime number dividing 6? No. So if you have a one prime number dividing an element, a number, this number must be this prime number to some power. Okay? Yeah? Is that clear? Is that clear or not? Okay. The harder part is clear, but the easier part is not. Like, is that okay? So the number theory statement is just if you have a prime dividing a number, if you have only one prime dividing a number, then this number is this prime to some power. Okay? Yeah, it's good. Great. Now, how do you prove this?
But it could be 0 or 1 in general cases, right?
Pardon me?
The M could be 0 or 1 in general cases, just not in this.
Exactly. Not in this. Well, it could be 1 here, right? Could be 1. M could be 1. But not 0.
M could be also 0 because R could be 1 and it does not.
No,
Actually,
if,
no, it has no.
if M
no
is 0,
prime.
then R has one element.
1 has no prime.
Divisors. Unless you consider 1 to be prime, which
No,
is not standard.
no.
Yeah. Because every statement you do is you will say let P be a prime different than 1. Let P be a prime, so it's not considered. Okay, how do you prove this? How do you prove this?
Use the same thing as group.
Sure, we could use the same thing as groups, but we could use rings. We have to use rings, right?
Yeah.
Prove. Let phi from Z denote, oh man, the unique ring homomorphism Zn cross Zm. What is the kernel of that? The kernel of that element is the kernel of that function is the characteristic times z, right? Now what is the characteristic? It's the order of the multiplicative identity, right? The order, or the characteristic, or the order of, what's the multiplicative identity here? It's the equivalence class of 1n. 1n. What is that in that case? What is that in that case? Groups, what do you know?
LCM.
Is in Zn plus, very good, is LCM Mn. What is LCM Mn in that case? If M and N are co-prime.
M times N.
Exactly, this is Mn over GCD Mn, which is Mn. Hence, what can I say about the kernel of phi? This Mn is bigger or equal to 2. I mean, you know this, the order here is bigger or equal to 2. So we can use the proposition that we have. Hence, what can I say? What can I say about the kernel of phi? It's equal to what? M and Z, right? The kernel of phi is the characteristic of the ring. What is the kernel of phi? M and what is exactly? Hence, ker phi is M and Z. First isomorphism theorem for rings. Z modulo ker phi, which is equal to Z modulo M and Z, is isomorphic to a subring of cross ZMZ, right? Now what is the size of this one? Mn. What is the size of this one? It's also Mn. So what can I say about these two? They are isomorphic, right? Hence, or we can write this hence phi of z is a subring of Zn plus Zm and phi of z is equal to Mn, right? Which is equal to the size of Z mod M cross Z mod M, right? Hence phi is surjective. So Z mod Mn Z is isomorphic to Zn as rings. Great. Oops. Any questions on this one? Yeah, you had a question, sir? You had a question?
Oh no.
Sorry. Yeah.
So you're saying that the identity is MSZ, just to clarify.
No, the set of element that map to 0, 0 is M and Z. Okay? Are we good here? Any question? Yeah.
Last time you taught the Chinese remainder theorem, it was an if and only if statement, and now it's not.
Very good. So if M and N are co-prime, then Z M N Z is isomorphic to Zn cross Zm. Now if M and N are not co-prime, are those isomorphic as rings? No, because they're not isomorphic as groups. So, very good, very, very, very good. Now, remark. If Mn is different than 1, then Z mod Nz cross Z mod Mz is not isomorphic or what are I saying? Z, M, and Z as groups. So if they're not isomorphic as groups, then they're not isomorphic as rings. Because any ring homomorphism is a group homomorphism. Hence, as rings, if and only if GCD Mn. Okay, great. Now, are we good here? Any questions? Yeah.
What's after it is not isomorphic to?
ZMN
Okay.
as groups. I mean, I can't even read that. Thank you. Okay, great. Are we good with this stuff? This characteristic business, is it good? Okay, what time is it? 12. I have 10 minutes. Okay, this characteristic stuff is good or not? Okay, so please revisit this. Study this very well. Know how to prove statements with that. I could give you small calculations with these. I could give you a proof of these, but you will get something there. Okay? Yeah? You will get a question on characteristic, whether it is a calculation or a proof.
How could the question be phrased?
You'll see. You'll see. Okay? Okay, I mean, let me now leave some stuff as exercises. Rings of characteristic 0. I mean, this is obvious reading. This is not very hard. Like R be a ring. R has characteristic 0 if and only if 1R does not have a finite order. Okay? That's obvious. Or should I do it? Do you want me to do it? I can do it, but I mean, is it clear? Do you want to practice it at home? Practice this at home. Practice this at home. It's good practice. Practice it. Just see how you feel with this characteristic business, and then maybe I'll do it next time. But just I want you to practice it. Yeah.
We just filled it out.
I mean, I can say verbally how to prove it. Okay. So if R has characteristic 0, this means that the kernel of your homomorphism is 0, right? From Z to R. This means that your homomorphism is injective. This means that the only element M such that M times 1R is equal to 0 is 0. So if M is positive, then M times 1R is different than 0. Okay? Now, let's go for the reverse.
No, that
Yeah.
doesn't say that one has finite order.
Does not have a finite order.
That does not have a finite order.
It
How
doesn't
does
have-
it say that?
Because if it had a finite order, you would have M times 1 is equal to 0 for some M.
So no m exists except 0,
Exactly.
and since R is a ring, but it's not necessarily a field.
No, R1 does not have an R plus. Is that clear? Thanks to the person who asked me about rings of characteristic 0. I mean, I totally had forgotten them, so last lecture they come and ask me about this. So yeah, so R has characteristic 0 if and only if 1 does not have a finite order. And the converse is also true. If 1 does not have a finite order, then for any m times 1r is different than 0. Except 0, except for m equals 0, and then boom. Okay? So prove it as an exercise. Now we'll move on to better stuff. Well, better or not better, I don't know. But still interesting stuff. So I mean the next 5 lectures will be dedicated to generalizing the arithmetic of Z to integral domains. So we'll do some arithmetic and integral domains. We'll see polynomials, and then we'll see some places where unique factorization fails. You cannot factor things uniquely. So we'll do that. Now, it's going to be a bit difficult. So I will be clear with you what parts to expect on the exam and what parts not to expect. But we'll just do this, okay? Great. So now we'll just talk about ideals, prime and maximal ideals. So I mean, I expect myself to be done with the material on Friday, next Friday. I'll be done with the material. Again, so it's not my bad that the exam has been scheduled on the very first day, very first hour. But, I mean, I'm honestly not very bothered by it because I'll grade fast and then return your grades fast. But I know for you it might be a problem. But I mean, I think it has a positive side that this is for the next 2 weeks. This is the only exam you'll study for, right? So you'll do well.
Wait, what does that mean? When is it?
It's on December 6th, no, the final.
Yeah, it hasn't changed, right?
I know it hasn't changed, but I'm saying for the next 2 weeks, this is what you'll be doing most likely. So I expect you guys to do well. Anyways, so prime and maximal ideal.
But so what we are doing right now won't be on the
No, it will be on the final. I'll be done next Friday. Polynomials. Monday, Wednesday, and Friday are polynomials. We can do some review or some calculations.
Yeah, good.
Okay? No, definitely. I'm not unreasonable to put material that is going to be covered on the final on 2 days before the exam. Yeah? Yes.
The what?
You have seen the 2 proofs on rings. Okay? Okay, so the 2 proofs on rings have been seen.
There's no more left, I guess, the rest.
Rings.
Yeah, we already seen the
2 proofs. No, there are 3 ring questions.
Oh, yeah, but one's calculations. Right.
Yeah, but don't underestimate calculation. Don't underestimate that. Okay? It could be. Yeah, so if that makes it feel better, yeah. We have seen the proofs of rings. The 2 proofs that are going to be there, we have seen them. I'll just have to double check and make sure. If I say nothing, means you have seen them. Okay? So you have 6 lectures on rings, and you have 2 questions from these 6 lectures. Okay? Again, I don't know, what else do you want me to do? I can give you the question, but I won't do that. But okay, so I mean, it's 6 lectures. I know every lecture is like 10 propositions, so that's like 60 propositions. But yeah. Okay, so again, and I mean, I have some time. Maybe I have 5 minutes. Maybe I can do this next time. But I want to tell you something. When you study for the proofs, don't read your notes and say, oh, I know how to do that. Because if you say, yeah, this is how you do it, and then you don't rewrite it, it's going to be bad. Especially if it's the first time reading it. So, what I would suggest, first try the theorem on your own. The first time, most likely, you will not be able to reproduce the proof. So what do? You go and read it. Now once you go and read it, don't say, oh, I got this. No, Once you go and read it, rewrite it. Rewrite it until you don't need your notes anymore. You don't need the recordings anymore. Make sure you master every single theorem. Make sure you know to write the proof of every single theorem. This is the way to learn the proofs that are being questioned from the notes, that are being examined directly from the notes or from the homework. This is how to go. This is the way to go because one, you will learn. Two, it will be in your head. If you write it like 5 times, you will internalize it. And then there's something. Don't try to convince yourself that you know it. Okay, I remember something when I had SATs, and you have this reading comprehension. These are difficult questions in general, in English. So, and you have these practice books, and you have the answer, in the back of these multiple choices. I would be stuck on a question and then glance, at the answer. And then, I fill in, I bubble in. And then when I count my marks, I'm like, oh man, I got 800 on 800. So I'm very good. So I could convince myself that I'm doing well. But then you go to the actual exam and then, you see that it's going to go terribly. So this is my advice to you. Just go and rewrite your proofs, rewrite your notes. Make sure to understand every step. You don't need any book, any other book than the notes and the homework. Focus on homework 7, 8, 9, and to a lesser extent, homework 6. Okay? 6, 7, 8, 9 should be mastered. You should know every single question, every possible group action that you have seen. I won't ask you a group action that you have not. I won't ask you a group action that you have not seen. Okay, so group action. All of the questions concern group actions that you have seen. Okay, I'll not ask you to come up with a weird action on your own. Okay, so everything's gonna be fair. I think. I hope so. At least I hope you will find that. And homework. Group action, co-set representation, that's going to be like I said yesterday, I think. So group theory part, you have maybe on 40, I would say 27.5 could be done with group actions. On 40 could be done with group actions. I'm not saying group actions is the only way, but if you really master group actions, then you get 27.5 on 40. On groups. Okay? Now, again, you should be able to rederive everything. The exam will take you 1 hour if you study it. If you study it, will take you 1 hour. Even less. If you know what you're doing, even less. Before, so my original exam, it was just made to, to just keep you sitting and make you rewrite proofs from the notes. Okay? It was, in my opinion, it was many proofs from the notes, and they were not the easiest. So you had to sit and write them. Now the proofs are not very long. I mean, we haven't done any long proofs so far. I mean, the proofs that were there, I didn't do them yet. So, and they won't be covered because I think it's a bit hard. But so, what I really encourage you to do is reread your notes and rewrite them. And I will post practice questions on calculations and on groups. Maybe, on groups on the review session I'll do them, but I won't post them. But for rings and fields, I'll post practice question on calculations. Don't wait for me to solve them. Solve them before. Because if you just wait for me to solve them and you don't redo them, you'll convince yourself that you know them. And then when the exam comes, you won't be able to figure them out on your own if you don't revisit them. Okay, so again, this is my advice. The exam is very, in my humble opinion, it's very fair and it should be done quickly. And again, go to tutorials. And examples I focus on in class, they're important examples, okay? If you see examples in the homework that are repeated, it's most likely because it's important, okay? Great, so see you all. Pardon me? What? Cheat sheet? Like an example?
You can put your own examples in your own cheat sheet.
Oh, like a formula, like a crib sheet? Oh. Good one, good one. Good one.